My dear students, we discussed about in the last class the addition of vectors. So what is addition of vectors? Addition of any two vectors A bar and B bar is defined only when the terminal point of the first vector coincides with the what? Initial point of the second vector. I told about this is, if I take this one as A, if I take B, if I take C, this is A bar, this is B bar, then this is nothing but what? A bar plus B bar. That is AC bar is equal to AB bar plus BC bar. Look here, AC bar is equal to AB bar plus BC bar. Means the terminal point of the first vector coincides with the what? Initial point of the second vector. Initial point of the second vector. So therefore, now this is the terminal point of the first, initial point of the second. This is for the first vector A bar. B is the what? Terminal point, and it's an initial point for the what? Second vector. So therefore, AC bar is equal to, this is what? A bar plus B bar. A bar plus B bar. So therefore, we discussed about earlier as addition of vectors satisfies a commutative law. That is A bar plus B bar. A bar plus B bar is equal to B bar plus A bar. Is nothing but parallelogram law of addition. Is nothing but a parallelogram law of addition. Similarly, we can also move on to the what? Vector addition satisfies associative law. Vector addition satisfies associative law. Or you can take it as vector addition satisfies associative law. That is A bar plus of B bar plus C bar is equal to A bar plus B bar plus C bar. So now let us start. If I take a parallelogram, let us consider AB bar is equal to A, BC bar is equal to B, CD bar is equal to what? C bar. Fourth side is left free. Finding the fourth side is nothing but what? Proving the associative law. So therefore, let us consider what? LHS. What is LHS? If I consider LHS, A bar plus B bar plus C bar, I have taken AB bar is equal to A bar. You take AB bar. Next you take what? B, that is B bar as what? BC bar. This is what? CD bar. By using the definition of addition of vectors, addition of any two vectors is defined only when the terminal point of the first vector coincides with what? Initial point of the second vector. So therefore, I can write AB bar, this is nothing but what? BD bar, correct? Now terminal point of the first vector coincides with what? AD bar. So therefore, AD bar is nothing but what? This is A bar plus B bar plus C bar. On the same lines, I can also consider that is RHS. What is RHS? The RHS is nothing but A bar plus B bar plus C bar. This is nothing but AB bar. This is BC bar. This is what? CD bar. Therefore, the terminal point of the first vector coincides with the initial point of the second vector. Once again, terminal point of the first vector coincides with the initial point of the second vector. We can write AD bar. So therefore, now you call it as 1. Now you call it as 2. This is A bar plus B bar plus C bar. This is nothing but you call it as 2. From 1 and 2. From 1 and 2, we can write A bar plus B bar plus C bar as A bar plus B bar plus C bar. Therefore, LHS is equal to what? RHS. So therefore, now we have proved, what we have proved is vector addition satisfies a what? Associative law. Meanwhile, as we have dealt on earlier, vector addition also satisfies what? Commutative law. So therefore, yes, we come across the two main discussions on the addition of vectors. Addition of any two vectors is defined only when the terminal point of the first vector coincides with the initial point of the second vector. Now, let A bar and B bar be two non-zero vectors. Then we can prove that the three identities, one is modulus of A bar plus B bar is less than or equal to modulus of A bar modulus of B bar. Next, we can also prove modulus of A bar minus B bar is less than or equal to modulus of A bar plus modulus of B bar. Modulus of B bar. We can also prove modulus of A bar minus B bar is greater than or equal to modulus of A bar modulus of B bar. These are the three important inequalities are defined with respect to the modulus in vectors. That too in vector algebra, that is vector addition of vectors. Now you consider AB bar is equal to A bar and BC bar is equal to B bar, and this is what? A bar plus B bar. Now I start. The proof of this one is, let AB bar is equal to A bar. Next, BC bar is equal to B bar by vector addition. By vector addition, AC bar can be written as AB bar plus BC bar. The terminal point of the first vector coincides with the initial point of the second vector. So therefore, I can write AC bar is equal to A bar plus B bar. Now, this is the vector treatment, addition of vectors. When AB bar is equal to A bar, when BC bar is equal to B bar, and AC bar is equal to A bar plus B bar by definition. These are the what? Directions of a vector. What about their magnitude? I can write AB is equal to A modulus of A bar, and that is BC is equal to what? Modulus of B bar. Right? Or else I can also write this is what? Modulus of AB bar is same as this, is same as what? Modulus of BC bar, as you please. Similarly, in the same fashion, we can also write, yes, AC modulus of AC bar is nothing but AC is nothing but modulus of A bar plus B bar. Now, as I told, addition of vectors, indirectly it supposes the triangular law of addition. So therefore, the terminal point of the first vector coincides with the initial point of the second vector, means indirectly it forms a triangle. We are finding the triangular law of addition. So therefore, I can write, yes, we know, now one side is always less than or equal to sum of the two sides, AB plus BC. Right? So therefore, now by using triangular property, so therefore what is AC? This is nothing but A bar plus B bar. This is modulus of A, modulus of B. Yes, we could prove as first identity as what? Modulus of A bar plus B bar is less than or equal to modulus of AB bar, modulus of what? A bar plus modulus of B bar. AC is less than or equal to AB plus BC. Modulus of AC bar is less than or equal to modulus of AB bar plus modulus of BC bar. Right? Okay. Now we proved the first conditions. In the same fashion, we can also go for what? The second one. What is that? Modulus of A bar minus B bar can be written as modulus of minus B bar. By using this property, I can write modulus of A bar minus B bar is less than or equal to modulus of A bar modulus of B bar. Therefore, modulus of A bar plus B bar, this is modulus of A under modulus, if any negative quantity, it becomes what? Positive. So therefore, we have proved modulus of A bar minus B bar, modulus of A bar minus B bar is less than or equal to what? Mod A plus mod B, right? Mod A plus mod B. Right, now coming to the third one is modulus of, yes, modulus of A bar minus B bar. I can write modulus of A. So this is equal to modulus of A minus B plus B, I can write. So therefore, now you can make this as a one bracket. Now this is nothing but, now modulus of A bar is less than or equal to modulus of A minus B plus modulus of B. You transfer to this side, this becomes modulus of A minus modulus of B is less than or equal to, this is, you call it as 1. In the same fashion, I can also write modulus of B bar is equal to modulus of B minus A plus A. This can be written as, this is less than or equal to modulus of B minus A plus A. So now you transfer this side, modulus of B minus modulus of A is less than or equal to B minus A. This is same as, now look here, modulus of B minus modulus of A is same as A minus B. This is 2, right? So therefore, now from 1 and 2, modulus of A bar minus B bar is greater than or equal to modulus of A minus modulus of B. Yes, under vector addition, we have proved the what 3 conditions. One is modulus of A bar plus B bar is less than or equal to mod A plus mod B. Modulus of A minus B is less than or equal to what? Mod A, that is mod A minus mod B, mod A plus mod B. Next, modulus of A minus B is greater than or equal to modulus of mod A minus mod B. So therefore, these are the identities we come across under what? Addition of vectors, right? So let us move in understanding scalar multiplication of a vector. Means you are multiplying a vector with a non-zero scalar. Remember, in definition itself explains the scalar multiplication of a vector is a vector. It is not a scalar quantity, it is a vector quantity. So therefore, now I can say right, scalar multiplication of a vector. I start, let A bar be a non-zero vector, X be a non-zero scalar. Then the scalar multiplication of a vector, then the scalar multiplication of a vector is defined as XA bar and is a vector, and its magnitude is, that is, a modulus of XA bar is same as X into modulus of A bar. Yes. What is the definition? The scalar multiplication of a vector. Let a bar be a non-zero vector, x be a non-zero scalar. Then the scalar multiplication of a vector is defined as xa bar. When you multiply any vector with a non-zero scalar, is once again a vector quantity. It is never be a scalar. If it is a scalar, no need to go for discussions. Since it is a vector and its magnitude is what? Modulus of xa bar, x into what? Mod a bar. Sir, when x is a positive, when x is a negative, yes, the direction of xa bar in comparison with a bar will be in the same direction or maybe in the what? Opposite direction, depends upon the value of x. If x is positive, a bar and xa bar having the same directions. If x is negative, then a bar and xa bar are having opposite directions, negative vectors. So therefore, let us have the what? Pictorial representation for this. If I take a bar, now this is nothing but, now look here, xa bar. So therefore here x is positive. I can also go for what? This is xa bar. X is a negative. Right? Now I can also go for, this is nothing but what? xa bar, where x is equal to 2. It is twice this vector. Its magnitude has been increased how many times? 2 times in the same direction. Now look here, next, I can also write roughly, this is xa bar, where x is equal to minus 2. Now x is negative. Now its magnitude has been increased by how many times? 2 times, but opposite direction. So therefore, the vector a bar and xa bar will have a what? Same direction, depends upon the value of x is positive or what? Negative. Followed? So therefore, x is positive or what? Negative. So therefore, now coming to, I can also write, now this is xa bar, where x is equal to f. Now I can also write, this is xa bar, where x is equal to minus f. Here, its magnitude has been decreased by how many times? Half of its. But this is also a vector. This is also a vector. Vector, 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 vector. Nevertheless, all these are vectors. It is quite obvious. When you multiply any vector with a scalar, it's what? Vector quantity. From this figure, logically, I am going to establish an important definitions in vectors of vector addition or vector algebra. That is parallel vectors and collinear vectors. Parallel vectors, the vectors which are parallel to each other, they are parallel vectors. The vectors which are lying on a same line, what they are? What? Collinear vectors. Yes, before going to what? Collinearity and parallel vectors, again, the scalar multiplication of a vector is once again a vector. Let a bar be a non-zero vector and x be a what? Non-zero what? Scalar. Then the scalar multiplication of a vector is defined as xa bar. So therefore, and is a vector quantity. So therefore, and its magnitude is what? Modulus of xa bar, x into mod a bar. Therefore, this is a bar, xa bar when x is positive. That is a bar, xa bar when x is negative. That is xa bar when x equal to 2 times its magnitude. Xa bar, that is x equal to minus 2, same direction, opposite direction. Now xa bar, x is equal to f. Now xa bar, x is equal to minus of. How they are in nature? This is parallel to this, 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 this is parallel to this. So therefore, now I can establish, now this vector is made equal to this under the condition A bar is equal to XA bar. Right? So therefore, now when any two vectors are said to be parallel, one vector can be expressed as scalar multiple of another vector. From the above figure, we can very well observe when any two vectors are parallel to each other, then one vector can be parallel to each other. Then one vector can be expressed as scalar multiple of another vector. That is, let A bar comma B bar be two vectors. Okay, other vector, that is A bar is equal to XB bar, where X belongs to R. Let A bar comma B bar be two vectors are said to be collinear or parallel vectors if they lie on the same line or parallel to each other. For example, I take A, B, C. This AB bar is A bar. This BC bar is what? B bar. You can very well observe A bar and B bar are what? Collinear vectors. A bar and B bar are what? Collinear vectors. If they lie on a same line, they are collinear vectors. Right? They are collinear vectors. Now, if I take another example, this is A bar, this is what? B bar. How they are in nature? They are parallel to each other. When any two vectors are parallel to each other, they are parallel vectors. When two vectors, they have a same line of action. What I said? If any two vectors are having the same line of actions or lying on a same line, then those vectors are what? Collinear vectors. What vectors? Collinear vectors. Followed? Now look here, as I told, A bar and B bar are two parallel vectors. So now the relation between them is when any two vectors are said to be either collinear or parallel, the common solution, common condition is one vector can be expressed as scalar multiple of another vector. Remember, my dear students, hereafter when any two vectors are said to be either collinear or parallel, one vector can be expressed as scalar multiple of another vector. In parallel vectors, A bar and B bar may be like vectors, may be unlike vectors. Now they are like vectors. I can also write A bar, I can also write what? B bar. But they are parallel. But having what? Opposite directions. So therefore under parallel vectors you get what? Two type of vectors, maybe like, maybe unlike vectors. Okay, now we discussed about the scalar multiplication of vectors and collinear vectors and parallel vectors. In scalar multiplication of vectors, I told already, now one vector can be, that is xa bar. Let x be a non-zero scalar, a be a non-zero vector. Then scalar multiplication of a vector is defined as xa bar is once again a vector. Its magnitude is x into mod a bar. And I would given some pictorial representation: a bar, xa bar, xa, that is xa bar, x is positive, x is negative, x is equal to minus 2, x equal to half, and x equal to minus half I have given. So all from the figures you can very well observe, we can establish in what? Very important definition: collinear and parallel vectors. From the above figures we have understood that when any two vectors are said to be parallel, one vector can be expressed as scalar multiple of another vector. A bar is equal to xb bar. So therefore now with this one I am going for definition of collinear and parallel vectors. Collinear vectors means what? If the vectors are having the same line of actions, the vectors are said to be collinear, or parallel vectors if they lie on the same line or parallel to each other, then those vectors are called what? Parallel vectors. For both the vectors we can very well observe the one vector can be expressed as scalar multiple of another vector, where x belongs to what? R. X belongs to R. Okay, right. After knowing the definition of collinear vectors and parallel vectors, now let us understand the position vector of a point P. Position right. Let O be the origin. O be the origin and P be a point in a plane or in a space. Then OP bar is called position vector of a point P. The position vector of a point P. So now look here, say for example, let O be the origin, P be a point. So now wherever I stand, this is my origin. Now some particular point I want to reach, that is taken as what? P. P be any point in the space. Converting that what? Directed line segment under vectorial representation is called what? The position vector of a point P. So therefore now the distance between the two walls is what? Some 2 centimeters, 10 meters or feet something. This is my origin. That wall is a required point. That wall is required point. So therefore the distance I want to convert with giving a what? Direction. That gives a position vector of a point P. Say for example, if we go to what? Come on, triangle. The triangle, this is A, this is what? B, this is C. This vertices is represented with position vector of a point. A is a point. These points are represented with what? Position vector. Where is O? You take this O. This is OA, this is OB, this is OC. O is a what? Free vector. When there is no restriction to for selection of initial point, that is nothing but free vector. When there is a restriction for a selection of an initial point or a terminal point, it's a localized vector. So therefore, now this is whenever any vertices are represented with what? O, OA, OB, OC, they are nothing but position vector of a vertices of a triangle or a parallelogram. ABCD, OA, OB, OC, OD. Where is O? This is O. OA, OB, OC. I am taking it. So therefore, now OP bar. Hereafter, whenever, wherever, if you come across OP bar, it represents what? The position vector of a point. So therefore, now if I write OA bar, it's a position vector of a point A. If I write OB bar, position vector of a point B. If I write OC bar, it's a position vector of a point C. If I write about AB bar, it's a vector side it is. If I write what? Come on, BC bar. This is also side. This is also what? CA bar. Now sides are represented with the vectors and points, vertices are represented with what? Position vectors. So therefore now you understood the difference between the position vector of a point and the what? Vectors. So therefore now with the help of this one is position vector of a point P, let O be the origin, P be a point in a plane, then OP bar is called the position vector of a point P. Position vector of a point P. Now, by using a definition of addition of vectors, this is a line segment. I am taking O, this is A, this is what? B. 3 points are there. So therefore, this I can write OA bar, AB bar. On this line, 3 points are collinear. Now look here, by definition of addition of vectors, yes, OB bar can be written as the terminal point of the first vector must coincide with what? Initial point of the second vector. OB bar is equal to OA bar plus AB bar by using definition of addition of vectors. So therefore, no. So OB is a position vector of a point B, OA is a position vector of a point A. Therefore, I can write AB bar transfer OA to what? LHS. Yes, we got it. Yes, what is that? AB bar can be written as OB minus OA. Remember, whenever the 2 points are given, we can construct a one vector. To get a one vector, you must have a 2 points, two position vectors of 2 points. So therefore, AB bar, for AB bar, A is the initial point, B is the terminal point. So therefore, every vector can be expressed as the position vectors of its extremities. Position vectors of its extremities. AB bar is equal to OB minus OA. OB minus OA. That is position vector of what? Terminal point minus position vector of what? Initial point. So therefore, I can also write CD bar, OD minus OC. Next what? Come on, SP bar, OP minus OS. Right. This is the, now how to express any vector in terms of its position of vectors of its extremities. Yes. Now, let us define the angle between the two vectors. Now look here. OA bar is equal to A bar. Here OB bar is equal to B bar. Be two vectors. Here we have defined OA and OB as a vectors, not as a position vectors. Be two vectors. Now, and theta is the angle between two non-zero vectors, two vectors and non-zero vectors and is denoted by A bar comma B bar is equal to this. A bar comma B bar is equal to theta. So therefore, and theta where 0 less than or equal to theta less than or equal to pi. Theta can vary from what? 0 to pi. Let us consider this is nothing but O, A, this is A bar, this is B, it's a B bar. Now this is nothing but minus A bar, this is nothing but minus B bar. So therefore, if this is theta, right? If this is theta, this is also what? Theta. As you know, the angle between this is 180, correct or not? So therefore, this angle is what? 180 minus theta. Therefore, this is also 180 minus theta. So therefore, now the angle between A bar and B bar is same as angle between minus A bar and minus B bar. They are in opposite direction. So therefore, from this one, what we can observe is, very first one is, angle between A bar and B bar is equal to minus A bar minus B bar is equal to theta. Then next I go for 2, the angle between minus A bar comma B bar, this is minus A bar and B bar, that is A bar comma minus B bar. I can write A bar comma minus B bar can be written as 180 minus theta. Right? So therefore, now we can very well, and also I can write angle between A bar comma B bar is equal to MA bar NB bar, provided M and N must be what? Positive. Why? Because the angle is independent of the lengths of the vectors. Say for example, if I give the what counter example, if I take A bar as a one straight line, B bar is another straight line. So therefore, angle between the two straight lines is independent of their lengths. So therefore, the angle between the two vectors is same as what? Angle between what? MA bar comma what? NB bar. Here, these two are positive, M and N must be what? Positive. So therefore, it may be 2A bar, it may be 3B bar, it may be 4A bar, it may be 100B bar. Angle is what? Same. So therefore, this is equal to what? Theta. Yes. Now we come across it about what? The angle between the two vectors. Let A bar comma B bar be two non-zero vectors. Theta is the angle between them. Then, if the angle between A bar and B bar is theta, the angle between minus A bar comma minus B bar is also a theta. Meanwhile, if total angle is 180, this is 180 minus theta, the angle between minus A bar and B bar is equal to angle between A bar and minus B bar. And meanwhile, the last one is, what is that? A bar comma B bar is equal to MA bar comma NB bar is equal to what? Theta. So therefore, what it represents? It represents the angle between the two vectors is same as what? Angle with what? 2A bar or 3B bar. It can be extended to any length. So that represents what? The meaning of this one is, yes, now we understood the angle between the what? Two vectors. Angle between the two vectors. One of the definition is two non-zero vectors or a corollary or anything. Two non-zero vectors. Non-zero vectors are said to be collinear. Then or else if and only if MA bar plus NB bar is equal to 0, and that is here M and N may not be, both are not equal to what? 0. M and N not equal to what? 0. So how, sir? The proof of this one is So when any two vectors, non-zero vectors, are said to be what? Collinear, we can also write as what? MA bar plus NB bar. How, sir? Let A bar comma B bar be two collinear vectors. There exists a scalar x belongs to R such that one vector can be expressed as scalar multiple of another vector. I can write minus 1 into A bar plus xb bar is equal to 0. Put m is equal to minus 1 and n is equal to x. So therefore, now this is 1. 1 implies ma bar plus nb bar. Here, at a time, both cannot be equal to 0, correct or not? M may be, now here, x is also not equal to 0. X may be equal to 0, may not be equal to 0, but m is not equal to what? 0. Therefore, ma bar plus nb bar. Hereafter, any 2 points are said to be what? Collinear. We can call it as, later we call it as what? It's a linear combination, correct or not? I mean, ma bar plus nb bar is equal to 0. Next notice, let A bar comma B bar comma C bar be the position vectors of 3 points capital A comma B comma C are said to be collinear if and only if it is xa bar plus yb bar zc bar is equal to 0 and x plus y plus z is equal to 0, where x, y, z belongs to what? R. 3 scalars. Now proof of this one is, let OA bar is equal to A bar, OB bar is equal to B bar, OC bar is equal to C bar, OC bar is equal to C bar. For some scalars, x comma y comma z, not all 0, right? Okay, not all 0. So now the proof of this one is, let OA bar is equal to A bar, OB bar is equal to B bar, OC bar is equal to C bar be the position vectors of 3 points capital A comma B comma C. So therefore, I can write AB bar is equal to, yes, come on, OB minus OA is equal to B bar minus A bar. One vector can be expressed as position vectors of its extremities. Why? It's a vector. These are the position vectors. Next, I can write, come on, AC bar. I can write AC bar. OC minus OA is equal to C bar minus A bar. One vector can be expressed as scalar multiple of another vectors. What we have taken? We have taken A, this is a B, it's a C. All are what? Collinear. So therefore, since AB bar comma AC bar are collinear, why collinear? When A bar, B bar, C bar are collinear, the vectors formed by the what? Three position vectors also what? Collinear. So therefore, collinear, there exists a scalar x such that one vector can be expressed as a scalar multiple of another vector. I can write, this is nothing but OB minus OA. This is nothing but what? X into OC minus OA. I can write this one as what? B bar minus A bar x into C bar minus A bar. OB is equal to B bar, OA is equal to A bar, OC is equal to A bar, OA bar is equal to A bar. So therefore, B bar minus A bar is equal to X into C bar, X into A bar. Okay, X into A bar. So therefore, we got it. X into B bar minus A bar, that is B bar minus A bar is equal to X into C bar minus A bar. C bar minus A bar. So therefore, B bar minus A bar is equal to XC bar minus XA bar. You transfer to that side. So therefore, or else brought to this one. So therefore, now XC bar minus B bar, yes, come on, plus 1 minus X into A bar is equal to 0 or 0 bar also, right? It's a vector quantity. Right side must be what? 0 bar only. So therefore, that goes without saying. Okay, when left side is a vector quantity, right side must also be what? Vector quantity. So therefore, now that is, I can write 1 minus X into A bar minus 1 into B bar, X into what? C bar is equal to 0. You call this as equation star. So therefore, put 1 minus X. Okay, now I have taken XA bar. Okay, now instead of this one is put 1 minus X is equal to M. Next, minus 1 is equal to what? N. And X is equal to what? P. Okay, I can write this one as star can be written as, yes, that is MA bar plus NB bar plus what? PC bar, right, is equal to 0. So therefore, now if I change this as X as some lambda, lambda can also be changed as what? Instead of, because already we wrote XA bar plus YB bar plus ZC bar is equal to 0. We have written X plus Y plus Z is equal to 0 in the statement. If once X is taken, we are not supposed to take as X. X is equal to, you take it as what? Lambda. Here also lambda. Here also lambda. Here also lambda. Here also lambda. Lambda. This also lambda. Here also lambda. Here also lambda. So therefore, 1 minus lambda is equal to M. That is X. Okay, as you please. This can be also taken as X. This can also taken as Y. This can also taken as what? Z. Or else I can write XA bar plus YB bar ZC bar is equal to 0. And M plus N plus P is same as what? Is same as X plus Y plus Z is same as 1 minus lambda. 1 minus lambda. Next minus 1 plus lambda. Plus lambda. Once again, I rewrite here. Once again, I rewrite. That is 1 minus lambda can also be taken as either X or what? M. Next, minus 1 can be taken as Y or what? N. Next, I can take lambda is equal to Z or what? That is M, N, P, right? As you please. So therefore, I can also write this one as XA bar plus YB bar plus ZC bar, and M plus N plus P same as X plus Y plus Z. This and this get cancels. This and this get cancels. Therefore, I can write X plus Y plus Z is equal to what? 0. Yes, we have proved what we have proved. When any 3 points are said to be collinear, we can write this as a linear combination. That is, linear combination XA bar plus YB bar plus ZC bar is equal to 0, or MA bar plus NB bar plus PC bar is equal to 0. That is, M plus N plus P is same as X plus Y plus Z is equal to, we got it as what? 0. Means sum of the 3 scalars must be equal to 0. Which I told. What I told, now X, Y, Z not all equal to 0. X may be 0, Y and Z may not be 0. X and Y may be 0, but Z may not be what? Equal to 0. So therefore, now sum of the 3 scalars must be equal to 0 and linear combination must be equal to what? 0. So therefore, hereafter, so we have come across it when any 3 points are said to be collinear. So therefore, linear combination is equal to 0. Means sum of the scalar multiplication of what? Points A bar, B bar, C bar vectors is equal to 0, and X plus Y plus Z is equal to 0. Yes, we come across mainly 2 theorems. What is it? When any 2 points are said to be collinear, MA bar plus NB bar is equal to 0, or XA bar plus YB bar is equal to 0. And meanwhile, when any 3 points are said to be collinear, so we have taken as what? Come on, MA bar plus NB bar plus PC bar is equal to 0, M plus N plus P is equal to 0, or M and P are the scalars, X, Y, Z are the scalars. So therefore, XA bar plus YB bar plus ZC bar is equal to 0, X plus Y plus Z is equal to 0, right? We understood how 2 points are collinear, how 3 points are what? Collinear.